Welcome to our series of short educational videos about important concepts of building performance. This video shows an example of a basic system analysis process of controlling indoor temperatures by an air conditioning system. We will also look at the concept of system balancing loops. For this discussion of the process controlling the indoor temperature with an air conditioning system, we look at the heat balance of our building. In our case, the heat balance of the system is described by the following flows of heat energy. The heat input, which in our case is a passive process where the indoor space is heated by a warmer outdoor environment. The heat output, which is in our case an active process where heat is removed from the indoor space by an air conditioning system. In our example process, we disregard heat that is generated inside our space and also aspects of latent heat transfer. We now introduce the concept of balancing loop in system analysis. A balancing loop is defined as a process where the system moves from one present state to an equilibrium state where the process involves some form of action. The balancing loop concept is an important assessment strategy of system thinking and analysis. The balancing loop considers a range of actions where the actions require some form of driving force. As we see in our example, driving forces can be self-driven, such as temperature difference where heat flows from warm outdoor to colder indoor, or driving forces which require some form of active energy input, such as an air conditioning system using electricity for removing heat from the space. In our example, we have two balancing loops, and these balancing loops are what we refer to as competing, as each balancing loop affects the performance of the other. Balancing loop 1. This represents heating of the room from the outside environment. Heat will flow from the warmer outside environment to the colder inside. The driving force is the temperature difference. This is a passive process, and the temperature difference is established by environmental conditions without the need of active engagement of energy at the building level. Balancing loop 2. Cooling of the room by the air conditioning system. Here, heat energy is removed from the indoor spaces by providing a thermal sink which is established by the air conditioning system. We now are looking at a basic process diagram. Balancing loop 1 is the warming of the room from the outside environment. This is a passive process as heat flows from the outside through the building envelope to the indoor space. The driving force is the temperature differential between the outside and the inside. As long as there is a temperature differential or delta T, heat flows from the warmer outside to the colder inside. The mechanism that regulates the rate of heat flow is the insulation provided by the building envelope, which impedes the heat flow. Balancing loop 2 is the cooling of the room, where heat is removed from the indoor space by an AC unit as long as the indoor temperature is above the set point temperature. The set point temperature is the temperature that is our target temperature, which the occupants adjust with a thermostat. As long as there is a temperature differential between warmer indoor temperature and the colder set point temperature, the air conditioning is operating. This image illustrates the thermal dynamics of the two balancing loops. The left diagram shows the dynamics of the room temperature acquiring heat from the outside. With colder indoor and warmer outdoor temperatures, the heat that flows through the wall from the outside and heats up the indoor space. Notice how the indoor temperature approaches an equilibrium, which is the outdoor temperature. Very noticeable is that the increase of the indoor air temperature slows as both temperatures approach each other. This temperature dynamics demonstrates the driving force of temperature differential which defines the conductive heat transfer rate. With larger temperature differentials, more heat is transferred. The right diagram shows the dynamic of the room temperature being lowered by the heat that is removed from the space by the AC unit. Notice that in our example, the indoor temperature approaches the set point temperature. In our example, the indoor air temperature is actively cooled and therefore approaches the set point temperature relatively fast. We now look at an illustrative scenario of the dynamics of the thermal behavior of our example air conditioning system. The set point temperature is defined by the occupants. The outdoor temperature is shown here as a simple linear line, where the outdoor temperature is constant early in the day, then rises during midday hours and then falls again at the end of the day. The indoor air temperature distribution is shown following a trend during the day that shows ups and downs of temperature movement. We see both balancing loops in action as the indoor temperature goes up and down during the day. From this example graph in the diagram, what conclusions can we draw about the cooling capacity of the AC? Is the AC capability of removing heat large enough to maintain the indoor space at or close to the target temperature defined by the set point temperature? We invite you to stop the video and think about this question for a moment. When ready, start the video again. Let's see what we can conclude from this scenario that we have shown in the graph. We might conclude that the air conditioning system is successful at lowering the indoor air temperature in the morning. When the midday higher outdoor temperatures set in, however, the cooling capacity is obviously not enough to keep the indoor air temperature at or close to the set point temperature. Once the outdoor temperature falls again in the evening, the indoor temperature is also going down. Although our example system and the assumptions are fairly simple, the system analysis tells us a lot about the thermal dynamics of our building system. We can use the lesson learned from these simple analyses and apply our system thinking to more complex systems. This completes our discussion. We now come to our self-learning assessment. Let's see how much you remember from our discussion. The self-assessment is an important step in the learning process. You can either contemplate and answer the questions yourself, or you can discuss the questions with friends or colleagues. It is proven that it is the best way to learn a topic by explaining it to somebody else. You see several self-learning assessment questions below. Please try to answer them. You might want to review portions of this video. Thanks for trying. And here are the questions. What are the two balancing loops when we think of an air conditioning in the building? What controls the heating of the room? What controls the cooling of the room? What is the trigger which starts the air conditioning to operate? This concludes our video. Thank you for your interest, and please join us again for one of our other educational videos.